Okay, we're going to look now at the derivatives of e to the power of x. This little chap here, e, and we've looked at that. It's like pi. It's an irrational number, sort of 2.7 thereabouts, and then ln x, which is log to base ex. We need to look at the derivatives of these different derivative laws altogether. Let's explore how they come about. Okay, so right, what I've put up here on the screen, just to explain, I've put up this graph here. I've asked it to sketch. Look here, this one here, y equals, or function of x equals ln x. Okay, log to base ex. So there's the log curve. Now on the curve, I've just got this point A, which is just floating around, and the coordinates of A are here and here. 4.78, currently 1.56. What I've also got is a measurement of the gradient at A. So the gradient is being measured. Just have a look at this. Alright, as A comes down here, look at it, it's super steep, goes further down, 14.7. Yeah, as we come through here, it flattens right out, doesn't it? There we go. Off it goes in that direction, and there we go. And it just flattens right out, just plateaus. Okay, and then you might have noticed there's another dot floating around here. Now this dot is doing this. I'll tell you what it's doing. It's actually tracking, maybe you've figured it out already, it's tracking this value here. It's tracking the gradient of the curve at that point. So you can see that it matches up vertically with A, so it's got the same x coordinate as A, but its y coordinate is, or its value, is the gradient of the curve at A. Okay, gradient of the curve at A, or the rate of change at A, or the derivative at A. Now all the same stuff. Alright, let's go back down here. When we get back down here, look at it skyrocket. Look at him shoot off up there. Righto. Now if I just put a trace on this point, let's do a trace on him. Trace the plotted point. Right now I'm going to drag A around. Tell me what's going on here. I might even animate A for fun. Animate that point A, speed him up a bit. Come on, we haven't got all day. Where's it gone? Here it comes. Okay. Whoa. Okay. So as we fly backwards and forwards, we are, okay, cut there. We are getting together. What's this here? What's this the curve of? What's that? What function is that? You hopefully know it's the positive branch of y equals 1 over x. So what we're getting here, if you think about this carefully, therefore if we plot the gradient of the log curve and if we plot all the points that match up to the gradient of this, then what we trace out is 1 over x. Remember, at this point here, this is my x coordinate on each curve is the same, and all I'm doing is looking at the value of the gradient and I'm plotting that up here. So I'm tracing that out, and what we end up with is 1 over x. So we can say that the derivative for log x, ln x, equals 1 over x. That stands to reason. The derivative of ln x will be equal to 1 over x. So just for example, alright, at this point x equals 0.31. We put 1 over 0.31 and we get 3.27. So we derive this to get 1 over x, we put in x, we get the gradient at that point. Make sense? So we'll make a note on that in a minute. Before we do, let's go and have a look at something else. Okay, let's have a look at this scenario here. Now what we've got is a similar situation. We've got a graph here which is, here it is here, a to the power of x. This a is my base. Now at the moment it's 1.51. 1.51 to the power of x. The point A floats around. It's got currently x coordinate, y coordinate, and also, as I did in the previous exercise, we are tracking also the gradient of the curve at this point. So this point here, this floater, is tracking the gradient of the curve at the point A. Now what I'm getting is that that's pretty close, isn't it? Like they're pretty close. So when the value of this function, so the y coordinate at A, as it increases, so does the gradient, doesn't it? See, the gradient goes with it. As it decreases, the gradient goes with it. So pretty close. Now, alright, so if I was going to track that out, it would be quite a close curve. If I just put a little trace on that, I trace that and I run around a little bit with A. You see, it's pretty close to it. It's not bad. Like it's closely resembling the function value. As the function value increases, so does the gradient. Okay, if less than 5 minutes remaining, I'm using a free version here. I'm gonna have to work fast. Okay, raise my traces. Now, what happens if I change this value of A? So A to the power of x. Right, so it's becoming A is 1.61 now. So what I'm going to do, I might just take the traces off here. Oh, it's not that one, it's this one. I'll take the trace off there, and I'll also go and just erase those traces. Alright, so as A increases, let's have a look at what happens to this floating point. Alright, as A increases, right, he's chasing him. He's getting closer. He's almost there. Oh, he's out of reach. I'm getting off the screen. Come back. Okay, have a look. Value of A, 2.46. Get there. Got him. Right, look at that, 2.72. What do you reckon that value of A is? You guessed it. That is the value of E. Alright, so let's just track that again. Right, what we are graphing, I'm changing, see how the graph changes because I'm changing the value of A. So as A changes, obviously this graph changes. At the moment it's 1.65 to the power of x. I increase the value of A, and this little point here is tracking the gradient of the curve. And it's very close, and it gets closer, and when you look, he's getting close, he's chasing him down, he's got him at 2.72. So at A equals 2.72, the gradient of the curve is exactly the same as the y coordinate at that point. Exactly the same. It's amazing. So let's have a little look at that. If I traced out then the gradient function, so if I did what I did in that last example, see how it comes off the curve there, back on him. I want to put a trace on him, trace on the plotted point. All right, I'm going to put this value here up to 2.72, and then I'm going to drag A around, and you can see, look at that, the gradient of the curve completely matches the function value of e to the x. So what we've discovered there is actually if you're looking to derive or find the gradient of e to the power of x, well, it's e to the power of x. It's unchanged. That's groundbreaking stuff. Hold fire there for a second. Okay, so after all that excitement, this is what it boils down to. That the derivative of excuse me, ln x, so log to base ex. Let's not forget what this means. Ln x is log to base ex. It's the same thing. You can write it either way. It's 1 over x, but it has to be base e, right? 1 over x. And the derivative of e to the x is e to the x. It doesn't change. And there's another way here of demonstrating that the derivative of ln x is 1 on x using what we know about e to the power of x, which I'll just show you. If we've got y equals log, I'm going to write it as log base ex. Okay, I can log out of this, can't I? I can write this as e to the y equals x, or x equals e to the y. Now if we accept that dx dy, because we were deriving x with respect to y, will not change when we derive it, and then the inversion or reciprocal law applies here when we flip this around the other way, 1 over e to the y. But e to the y equals x, so I could write that as 1 over x. So if I start with y equals log ex, then through that process we can show that dy dx equals 1 over x. It's just a nice little bit of an algebraic way of doing it. We saw it the graphical way, which is also quite neat. Okay, a couple of examples and then we're done. Alright, f of x is 3e to the power of x. Then what is f dash x? Well, e to the x doesn't change, and the constant at the front doesn't affect things, so it's just 3e to the power of x. Okay, so the derivative of any constant by e to the power of x will be that exact same function. Right, so f dash x here, we deal with x squared in the old-fashioned way, 2x. ln x, that goes to 1 over x. And so there's our derivative of x squared plus ln x. And the third one here is just to recognize that this, well, if you write it another way, if you've got e there and e there, then this is equal to 3x. So f dash x of 3x is just 3. A couple of straightforward examples, and I'm looking forward to seeing how you go with exercise 7H, which starts on page 209. It's not a long exercise. We'll do all the questions there, so you can get started if you wish. Otherwise, we'll get going on that when I see you next.